This is gravimetric analysis to accompany the lab for this week, Monday. So before we really understand what's going on with gravimetric analysis, we need to understand what's going on with precipitation. Hopefully you recall the #1 solubility rule from Chem, which is like dissolves like. We can actually get pretty far with this rule in our understanding of how precipitation works. We certainly understand that when we have nonpolar things, those are going to dissolve nonpolar solutes. And when we have a polar solvent, it's going to dissolve polar solvents and solutes, and those don't really mix. Of course, we can also have ionic solutions, which are going to be even more polar than water. And eventually, we can actually precipitate things out that are too polar to stay dissolved in water, and we precipitate out ionic solids. So when we do gravimetric analysis, we're really trying to balance between usually water and either precipitating out nonpolar things, we'll talk about that at the end of the chapter, and precipitating out polar things. And that's where we're going to focus most of our time here. So how does precipitation actually occur? Reactions only are going to occur towards equilibrium, which means for us to have precipitation, we have to have more concentration of the ions in solution than are actually soluble. So we have to be above the solubility product, or the solution must be supersaturated is another way of saying that. So when we start to precipitate, we're going to have some sort of particle of dust or maybe a scratch in the glass, something to start forming our precipitate around. Our precipitate doesn't, precipitate without any sort of impetus, and so we have to have something for it to start. Sometimes we'll even use seed crystals to start that precipitation. So say we have a bit of dust, we're going to start to have that negatively charged dust particle attract positive particles. In the case of our lab, we're using silver chloride, so we start to see silver come around. And once we start to build up silver around the dust particle, we've started nucleation. That's starting of a new crystal. Of course, we can continue to grow that crystal with particles like so. We can have more chlorides added into the solution. And eventually, we can also have a new nucleation as well if we have other dust particles. So we're always going to try to balance between nucleation and particle growth. We want to make sure that we have the possibility of nucleating, but we don't want to nucleate very many particles because we want to make sure that our crystals grow as big as possible. If we don't have very big crystals, if we end up having colloids instead, very small particles that stay suspended, rather than crashing out of solution, then we can oftentimes have lots of problems with impurity. So we also end up having a very difficult time to filter them, and they're, because they're so small. And so let's think about how exactly that's going to happen. Generally, we're going to have this very small particle, and as we start to build up this particle, we're going to have excess chloride, so it'll be negatively charged. Those particles won't really want to interact with each other. But as we continue adding more and more silver, we're going to start to have an excess of silver. Now we have a positive charge, and now the particles still don't want to interact. So really we want to be in that kind of Goldilocks zone where we have a balance of chlorine and silver so that we have a good chance of those colloids interacting. So the lower we can keep the excess of whatever we're precipitating with, the better chance we have of keeping those colloids close together and filtering them well. We can also increase the electrolyte concentration, so increase the number of other charged particles, and that can make a huge difference because it allows us to break up some of that crystal interface that we might see from having regularly spaced particles like the silver and the chloride. Either way, if we have any sort of excess silver on the outside, we're going to end up building up the nitrate as well. And if we're using silver nitrate as our precipitant, as we are in the lab. And so now we have what's called an electric double layer. And that double layer is going to create a high amount of stability in that colloid and keep it from forming together. So our goal then, if we have a colloid, is to coagulate the particles. So essentially eliminate that double layer. Again, the ways that we can do that are decrease the excess of the precipitant, the excess silver nitrate, or increase the electrolyte concentration. That works temporarily, but eventually we're going to have to filter our colloids. They're going to run through with water, and when that happens, our double layer is going to come back. because we're going to decrease the electrolyte concentration. We're going to start to see whatever remainder nitrate and silver is in solution pop back on. That's called peptization, when we go back to the colloids with the double layers, the separate colloids. So we want to avoid that as much as possible. So one way that we avoid that, if you've noticed, our silvers along the outside have changed to hydrogens. If we wash with this acid instead of just DI water, we're able to keep the electrolyte concentration high, and we're even able to replace some of those silvers with hydrogens. And when we do that, it's going to destroy the stability of that double layer. So then the nitrates will go away, and we're a lot more likely to be able to purify without all the impurities. Now, there are lots of different impurities that can come along when we have colloids. So we're going to talk about 4 different types of impurities. The first of which is adsorption, not absorption, adsorption. Notice the spelling. So adsorption is because we have a layer along the outside of whatever colloid crystal that we're starting to form, we are going to have charged particles that can adhere to the surface, absorb to the surface. And so we might get something like the sodium that's going to come along for the ride, and then we'll have excess sodium in the crystal, something that we're not trying to measure, and it'll generate some error. We can also have mixed crystal formation. Notice there's a cadmium now right next to that dust particle left of the center. That cadmium will fit into the crystal lattice. We end up having a different ion than what we expect in the crystal lattice. Usually that comes when the ion's pretty similar to the same size. Now we can also have occlusion. Now occlusion happens when the crystal is forming. We might have started to form our crystal and we have an open space in the center of our crystal, and we might get a different ion in there that doesn't really fit so well, like an H+, much smaller than the silver. Now, normally that wouldn't be an optimal interaction, but if the crystal is growing really, really fast, we can start to see all these other pieces line up into the lattice, and then that lattice get closed around the particle. We call that H+ then an occluded particle, and again an impurity. We can also have an entrapment. It's a little bit harder to see on this scale, so we want to go back to where we have 2 separate nucleated particles. Entrapment's when we have those particles coming together and we have an ion that's trapped between. So we end up having the sulfate trapped between the silvers instead of a chloride, for example. Now, one of the ways that we can avoid that is by practicing homogeneous precipitation. This really only works in some cases because we have to have a reaction that's going to form whatever precipitant we need. So if you think about titrating in any sort of precipitant into a solution, we notice that as we add things into the Erlenmeyer flask, we're going to have drops that come into the water. Those drops are going to be very high in concentration of whatever precipitant we have. So even though our overall concentration is probably low, our local concentration is very high. And so we're very far away from the saturation point, and that encourages nucleation rather than particle growth. So if we want to avoid that, we're going to try to create a reaction that creates this small amount of precipitant everywhere in solution at once in very low concentrations. So we can do that to generate things like hydroxide, phosphate, oxalate, sulfate, carbonate, H2S. So there are lots of different things that can be generated by reactions in the solution in order to precipitate. And that's a much easier way of making sure that your crystals are going to grow bigger rather than small colloids. So that about sums up how we deal with or think about gravimetric precipitation of ionic species. But now we want to go back and think about how we deal with this nonpolar species. So if we have any sort of metal that's trapped in solution, generally we think of that hydrated with a bunch of waters, as you can see in this figure. Now the idea behind nonpolar precipitation is that we're going to take off those waters so we don't stay dissolved, and we're going to replace it with an organic molecule that's going to bind in multiple locations across the same metal. We call that a chelating agent. If we take a chelating agent, we can wrap it all the way around the metal, and we call the entire complex a chelate. Now, if we wrap a nonpolar thing around that polar metal, Now it no longer is going to interact with water in the same way, and we can precipitate it out that way. There are many common chelating agents. One of the most common is EDTA, ethylene diamine tetraacetic acid, but the specificity of the chelating agent is going to be really important to make sure we don't precipitate out metals that we don't want along with the metals that we do want. And that is it for our gravimetric analysis.